This is the physical interpretation of the mean value theorem. If we consider, if we recall the previous example, you can say that our function is f of x equal to x square, and we consider this function in 0 2. Okay, what we have proved is if you consider f of 0 is 0 and f of this is our f of 2 and this is our f of 0, we find a point 1 such that f dash 1 is equal to f of 4 minus f of 2 minus f of 0 divided by 2 minus 0. Okay, so that is at the point 1 you can draw a line like this, and at the point 1 you will get a tangent whose slope is same as the slope of the straight line. Okay, so this is what we have proved here. So this quantity gives the, if you consider the interval 0 2, this quantity gives the average rate of change of f over 0 2, and this will give the instantaneous rate of change at the point 1, the rate of change of f. Clear? So the physical interpretation is, if you think of the number f of b minus f of a divided by b minus a as average change in f over b, ab, and f dash c is an instantaneous change, then the mean value theorem says that at some interior point, the instantaneous change must equal to the average change over the entire interval. Okay, this is the physical interpretation of mean value theorem. Now we have a theorem. If f dash x is equal to 0 at each point of an open interval AB, then f of x is a constant. Okay, so in order to prove f of x equal to c, that is a constant over interval AB, we consider interval AB first. Then if you choose any x1 and x2, any 2 point on open interval AB, we have to get f of x1 equal to f of x2. Okay, then we can say that f is constant along this interval. Okay, if we choose any two arbitrary point, this x1 and x2 are not particular points, arbitrary points. If we choose x1 and x2, any x1 and x2 from this interval, we have to prove that f of x1 equal to f of x2. So let x1 comma x2 be two arbitrary points on open interval AB. Okay, then we can consider an interval, okay, with this x1 and x2 as endpoints. Then f is, then we can say that f is continuous on x1 x2, the interval x1 x2, and differentiable on open interval x1 x2. There, so by therefore by mean value theorem, we can write there exists C belongs to open interval x1 comma x2 such that f dash C equal to f of x2 minus f of x1 divided by x2 minus x1. Okay, this implies what is f dash C? F dash C is always 0. That is our hypothesis. F dash C equal to f dash of x equal to 0 at each point x in between a and b. Since the C is in between a and b, you can say that LHS will be 0. Then the numerator f of x2 minus f of x1 by x2 minus x1 is equal to 0. So this implies f of x2 minus f of x1 is 0. Hence f of x1 equal to f of x2. So we can call at any 2 point x1 and x2, f has the same value, say some capital C. So this shows that f of x equal to C for all x belongs to open interval AB. So this is an application of mean value theorem. Now we have another consequence of the mean value theorem, functions with the same derivative. Okay, Suppose we have two differentiable functions f and g with we have f and g with f dash x equal to g dash x. That means the derivatives of these two functions are the same. Now we will prove that f of x and the relation between f of x and g of x. F of x equal to g of x plus c. For this we define h of x first. H of x equal to f of x minus g of x. Clear? This implies h of x, h dash x equal to f dash x minus g dash x, and this is equal to 0 for all x belongs to open under AB. Then the previous theorem shows that whenever the derivative of a function equal to 0 at all the points x belongs to AB, we can say that that function h of x is a constant. So this h of x, the function h of x is equal to some c for all x belongs to AB. So this implies what is h of x? H of x is defined as f of x minus g of x. So we have f of x minus g of x equal to a constant for all AB, for all x belongs to AB. So consequently we can write f of x equal to g of x plus c for all x belongs to AB. Okay. So this proves the second consequence. Now we have an example, example 5. Find the function f of x whose derivative is sin x and whose graph passes through the point 0, 2. For this we will use the previous consequence of mean value theorem. We know that whenever f dash x equal to g dash x for all x belongs to AB, open interval AB, then you can write f of x equal to g of x plus c for all x. Okay, so we know that we are given that f of x derivative of f of x is sin x. So that is f dash x equal to sin x. This is the given quantity. Then this implies f dash x equal to derivative of, that is d by dx of minus cos x. Right? So we can put this minus cos x x g. So f dash x equal to g dash x, where g of x equal to minus cos x. Okay, g of x equal to minus cos x means derivative of g of x equal to sin x. So this implies f of x equal to g of x plus c, that is minus cos x plus c for all x belongs to any interval, or you can write it as r if no interval is specified here. So this implies f of x equal to minus cos x plus c, and we are given that 0, the graph of the function passes through 0, 2. So whenever x equal to 0, we can say that the value of the function cos 0 plus c is 2. That is the meaning of this. The function passes through 0, 2. That means whenever x equals 0, you can get the function value is 2. So f of 0 equal to 2. That is the condition. That means minus cos 0 plus c equal to 2. This implies minus cos 0 is minus 1. So c is equal to 2 plus cos 0. Cos 0 is 1. So that is equal to 3. So our f of x. Okay, f of x equal to minus cos x plus 3. Okay, this is our function. This completes the section mean value theorem. Next onwards we will move on to the next section.